Okay, let's jump back to the way the book does it. We stopped here. This is back to the equations in the book, looking at the surface temperature in terms of the solar flux and the albedo divided by the Stefan Boltzmann constant sigma Sv. So this is the relation we had already derived. But then you add complications to it by remembering that the atmosphere is not, or the Earth's surface is not a perfect black body. So it's going to have an emissivity which is going to be less than 1. Then the outgoing long wave radiation is going to be epsilon of the mean, global mean, times the Stefan Boltzmann constant times the emissivity temperature. And this should be epsilon m here. It's a mistake. So it's 1 minus epsilon m times sigma Sv of the surface temperature. So there is an atmosphere emitting at its emissivity, and the surface is emitting at 1 minus epsilon m, and it's going to be balanced by the energy received from the sun, where not only does it have a albedo, but the atmosphere is now not completely transparent to the shortwave radiation. It has an emissivity with absorptivity with respect to shortwave radiation. We will see that this happens because of clouds, because of aerosols, etc. So atmosphere is not allowing all the shortwave to pass right through and get to the surface. It has a absorptivity as well. So this relation is derived in an older book that Judy Curry and Peter Webster wrote. I think you can look that up. So this is the balance that has to happen at the top of the atmosphere. So atmosphere is emitting something. The surface is managing to reach the space directly through places where there are no clouds, like deserts, and that's going to balance the energy that's coming in terms of the short wave. If you go to the surface, obviously surface is emitting at its temperature. It's receiving or it's also got an absorptivity of epsilon m, so we are combining the two here. So, and then it's receiving the solar coming in depending on the absorptivity of the atmosphere. So there is a balance that has to happen at the top of the atmosphere, which includes the energy balance of the outgoing long wave from the surface and the short wave absorbed in the atmosphere. And there is a balance at the surface where it's receiving long wave from the atmosphere, emitting its long wave, and receiving short wave through the atmosphere. Okay, the expressions look complicated, but just remember the previous simple derivation that I showed. This looks more complicated because we have added the emissivity of the atmosphere and its absorptivity of shortwave radiation coming in as well. So that gives us a slightly more complicated expression for the surface temperature in terms of, again, solar radiation, albedo, emissivity at black body temperatures, and absorptivity to solar radiation. Okay, the story remains the same, that the greenhouse effect makes the Earth's surface warmer than it was if it was not given this greenhouse blanket. That's why increasing greenhouse gases is giving us global warming, and that's what all the heartache has been about. Okay, this is the figure again from the book, looking at the outgoing long wave from the surface with its emissivity, what is coming from the surface, what the surface is receiving from the atmosphere, and what the atmosphere is receiving in terms of shortwave, and what it's transmitting to the surface. So the two complications are this emissivity and this solar absorptivity. Okay, looking now in terms of emissivity, going obviously from 0 to 1. This is going to absorb all the energy and emit it back. This is going to absorb the energy and just keep it. Okay, so here is the albedo. and it's worth looking at the range of temperatures. So here is the diagonal line that is 273 degree Kelvin, 273 Kelvin, we don't say degree, and it's getting colder here, so that's the yellow region, and we're getting warmer here. Obviously the current temperature of the earth is up here at 288, and these are the various pathways that could have that the earth's evolution could have taken, starting from here, which is the solid circle matching an albedo of 0.3 and an extremely small sensitivity. You can think of this as a primitive surface temperature when the earth was evolving, and then various pathways it could take depending on the emissivity and the albedo. Okay, so this amounts to an emissivity of 0.7 and an albedo of 0.3. Obviously this is a question that is critical in terms of what clouds will do with global warming. For example, if global warming increases the temperature obviously and increases humidity because warm temperatures hold more water vapor, and what will the clouds do? Will clouds get brighter and reflect more sunlight and basically compensate for the greenhouse effect of warming? Or will high clouds increase, for example, which tend to warm because they allow short wave to come in and they trap some of the outgoing long wave? So clouds are a big unknown, and they are very complicated, as we will see later on, and the big unknown in terms of their role as negative or positive feedback to increasing greenhouse effects because of anthropogenic activities has to be understood. Let me just run through this as well then. Water vapor pressure and temperature. We already looked at the Clausius-Clapeyron, which is for saturation humidity levels. So water vapor pressure for a given temperature when the parcel is completely saturated. So that's this line. We often look at it as a linear scale or a log scale. So you can see the exponential relation here for December, January, February, and June, July, August. Saturation temperature doesn't show a difference, much difference here. But if you look at the equator and at 45 degrees north and at 70 degrees north, obviously as you go to higher latitudes, the mean temperatures are lower, and the amount of water vapor or the water vapor pressure is going to be much lower. The numbers on top here are the surface pressures in hundreds of hectopascals. Okay, so this is 1000, which is basically surface, 900, which is in the middle of the planetary boundary layer, and so on. And if you look at the same pressure here, you are at a much lower temperature and water vapor pressure, and same for the high latitudes, mid latitudes. What does it mean? Basically, even though the atmosphere is not saturated, you can see that the temperature vapor pressure curves are essentially parallel to Clausius-Clapeyron. So Clausius-Clapeyron is working in its full glory even when the atmosphere is not fully saturated. Okay, this becomes critical as we will see later on. We'll come back and look at the water balance or the distribution of water in zonal and meridional directions in the atmosphere. Okay, so we looked at rainfall before. Now we'll look at water vapor distribution itself, because that corresponds to the heat exchange as well as the latent energy that's there. If you condense that water vapor into rain, let's say, you're going to release energy, which is what drives the circulation, right? So this is what the hydrologic and heat exchange processes are. Okay.